Astra, an interactive general world model. We are diving into a really crucial piece of research today.
Absolutely. This one feels like it's defining the next big leap in generative AI.
Right. We're moving beyond just making these impressive but, passive video clips.
To something that's actually an interactive, long-horizon world simulation. It's all about control.
And consistency. And getting it all to work in one single framework.
That's the core of it. Astra is designed specifically to predict these long-horizon futures for all sorts of diverse real-world systems.
So we're talking about things like autonomous driving simulations.
Exactly. Or, complex robot grasping precise camera movements, but over really long periods. And the key is how they fuse that high visual quality you get from diffusion models.
With the temporal consistency you absolutely need for a continuous simulation.
Right. And they do that with what they call an autoregressive denoising architecture.
Okay, so for the short form edit, let's nail down the 3 critical technical bits you really need to know about this paper.
Okay, first up is the Action-Aware Flow Transformer Adapter, or ACT adapter. This is basically the mechanism for injecting precise, real-time actions into the model.
So how you tell the car to turn.
Exactly. Second, they introduced noise-augmented history memory. This is a really clever noise-as-mask strategy they use during training.
And that's to overcome something they call visual inertia.
Yep. It forces the model to actually pay attention to the action signals, not just its own memory. And then finally, you have the modular mixture of action experts, or MoAE.
Which lets the model handle all these different kinds of inputs.
Exactly. It unifies everything, which gives it this incredible versatility across different apps.
Okay, let's really establish why this research was even necessary. I mean, we've all seen Sora. We've seen these phenomenal text-to-video models. So for the AI researchers listening, why are these amazing generative models just not enough if your goal is a real interactive simulator?
It all comes down to one thing: interactivity. That is the defining property of a world model.
And current models are passive.
Totally passive. They produce these stunning, short, self-contained clips from a static prompt. They generate a plausible outcome, but they can't adapt on the fly.
So if you pause the video and say, okay, now the car turns right,
the model has no idea what to do with that. It just doesn't have the architecture to process that kind of mid-rollout control and then, generate a coherent continuation.
So they're great at generating a kind of self-fulfilling prophecy from the start, but they can't handle real-time cause and effect.
That's a perfect way to put it. They simulate the world like a movie, not like a video game.
Right.
And the core technical struggle is, it's twofold. First, the longer your sequence runs, the more errors accumulate. You get temporal drift, the model just gets lost.
And the second problem?
How do you successfully integrate a complex, continuous action vector like a 7D robotic pose into a model that was basically built for text?
So Astra's big architectural choice to solve this was this autoregressive denoising paradigm.
Right. They take a pre-trained video diffusion backbone, which is already great at visual fidelity, and then kind of repurpose its flow matching ability.
To predict the next chunk of video.
Exactly. To predict ZT+1, conditioned on the history say. It turns a single shot generator into a continuous chunk-by-chunk prediction engine.
But now you have to get the steering wheel command or the robot grouper command into that engine.
Which brings us to their first big innovation, the ACT adapter.
Okay, let's get into the architectural trick here. We know diffusion transformers, or DITs, are almost entirely optimized for just making incredible visual output, right? Mostly guided by text.
Through cross-attention.
So if you have this highly optimized frozen DIT backbone, how on earth do you inject a precise action signal, which is totally different from text without, corrupting all that knowledge?
Yeah, that's the core problem. The original DIT is like this powerful engine designed to take a text description, a car on a mountain road, and make a video. It has no input port for real-time controls.
The ACT adapter is that new port.
It's more like a specialized, a low-overhead transmission system, instead of trying to retrain the whole engine.
They just do this surgical augmentation?
Exactly. They insert a lightweight adapter module, and this is just a single linear layer initialized as an identity mapping after each self-attention block in the transformer.
And that's how they avoid catastrophic forgetting. The huge generative part of the model stays frozen.
Right. The knowledge is preserved. And the injection mechanism itself is surprisingly simple.
What is it?
It's just element-wise addition. An encoder processes the action vector, aligns its features with the video latents, and then that feature is just added element-wise. at every single transformer block.
So that choice addition versus cross-attention, that's really critical for the technical audience here, isn't it?
It's huge. If they had used standard cross-attention, it would add way more computation, and more importantly, it would force the whole model to rethink how it processes inputs.
Potentially destabilizing that frozen backbone you wanted to protect.
Right. The additive injection is just so much more parameter efficient, and it isolates the causal path. And to really sharpen that control, they add action-free guidance, or AFG.
Which is like classifier-free guidance, but for actions?
Exactly. During training, they just randomly drop the action condition. That forces the model to learn what happens with and without a specific command.
And because of that dropout, during inference, you can calculate this guided velocity field. You can use a high guidance scale, like 3.0, to really amplify the effect of the action.
Right. It stops the action from being just a soft suggestion and makes it a hard command. It turns fine-grained control into an immediate, high-impact response.
Okay, so that brings us to the next big problem. The ACT adapter gives us precise control, but that's useless if the system is too slow to react.
Right.
Which leads to this fascinating, almost counterintuitive problem they called visual inertia. Can you explain that contradiction?
Yeah, the contradiction is between consistency and responsiveness. So to get maximum temporal consistency, stable visuals, no jitter, you need a long historical context. You want the model looking back at the last 3 to 5 seconds.
If the model is trained on typical real-world data, where most motion is smooth, a car just drifting in its lane,
then it learns to trust that visual memory too much. It starts to over-rely on those past frames.
And ignore the new command.
Exactly. If you suddenly command a sharp right turn, the visual memory acts like inertia. It slows down or just plain ignores the command because the visuals are so strongly suggesting go straight.
So the model is basically saying, look, I've seen a straight road for 10 frames, so I'm predicting another straight road frame no matter what this steering vector says.
That is the visual inertia problem in a nutshell. And their solution to this, without shortening the history, which would kill consistency, is the noise-augmented history memory.
Using this noise as mask strategy. Okay, this is the really clever part. Why inject random noise into the conditioning frames?
It's a genius use of distraction. Instead of the usual approach, like totally masking or dropping visual tokens,
they just mess with them.
They inject random noise directly into the historical frames the model is conditioning on. This noise intentionally blurs or, degrades the clean visual information in the memory.
It's like blurring the windshield just enough that you can't totally trust what you remember seeing a few seconds ago.
That's a perfect analogy. By corrupting the visual context, you're forcing the model to look somewhere else for the information it needs to predict the next frame.
And that somewhere else is the action signal from the ACT adapter.
Exactly. You're training it to integrate that causal action cue much more strongly. The visual data gives you the context, we're on a road, but the action vector gives you the dynamics, we're turning right now.
And this is so critical because they still need that long history.
Right, and they use compression techniques to push that history out to 8 or even 10 seconds. The long horizon gives you stability, the noise gives you responsiveness. It's a really complete solution to a chronic problem.
So we have precision from the ACT adapter, responsiveness from the noisy memory. The last piece of the puzzle is versatility. If this is going to be a general world model, it has to handle wildly different inputs. How do you unify a continuous 7D robot pose with, say, a discrete keyboard W press?
And that's the job of the mixture of action experts, the MoAE. Real-world systems don't have one standard control panel, right?
Right.
So MoAE provides this crucial modular framework to unify all these completely different signals.
So this is where the system translates any command into a universal language that the ACT adapter can actually process.
Exactly, but it does it with specialized pathways. First, all the different action types, camera pose, robotic pose, keyboard commands, they all get mapped into a shared feature space using these modality-specific projectors.
Which standardizes the format.
Right. And then, and this is the key part, it doesn't try to use one giant network to understand everything.
Which would just dilute the expertise.
It would. So instead, a router network calculates these gating scores and dynamically picks the top K relevant experts. And these experts are just independent MLPs, each specializing in a different type of action.
So the system is smart enough to know that if the input is a robotic joint angle, it should activate the manipulation expert and just let the vehicle navigation expert stay dormant.
That specialization is the whole point. It ensures you maintain precision because you're not forcing the same weights to learn how to interpret a mouse click and a complex quaternion rotation.
It makes sense. It improves generalization, keeps it efficient, and that final routed output is what feeds the ACT adapter.
Precisely.
Okay, so let's see how this whole pipeline performs. They benchmarked it on Astra Bench, which is built from these really diverse, high-stakes environments. Yeah. You've got new scenes for driving, RT1 for robotics, almost 400,000 videos.
Yeah, a massive data set.
So what does it all mean when the rubber meets the road?
Well, the quantitative results really confirm that the synergy of these three innovations works. When you compare Astra against strong baselines like WAN 2.1 or WinMe, it's consistently state-of-the-art across all 6 core metrics.
But let's focus on the metrics that really matter for interactivity.
Instruction following and motion smoothness.
Okay.
So look at instruction following. Astra scores a 0.669. That's significantly higher than competitors, which really struggle with the complexity of these inputs.
And that high score is direct proof that the MoAE and ACT adapter are working together perfectly.
It is. And then you have the near-perfect motion smoothness score of 0.989. That's the proof that the noisy memory trick worked.
It shows they got responsiveness without sacrificing that temporal coherence.
Exactly. The model learns to follow these abrupt, action-driven changes smoothly, which has always been the big trade-off in these systems. And for the audience that's really focused on raw numbers, the camera motion prediction was exceptional. Lowest rotation and translation errors.
1.23 rotor and 4.86 transfer.
Yeah, which just validates that the architecture is controlling the dynamics accurately, not just plausibly.
The ablation studies were also really telling. I mean, they confirmed all 3 components are essential. What was the most dramatic drop when they removed something?
Oh, by far it was removing the noisy memory. The instruction following score just plummeted from 0.669 all the way down to a dismal 0.359.
Wow.
It's just massive validation for its role in forcing the model to overcome that visual inertia. Removing the action-free guidance also really hurt responsiveness, which proves you need AFG to make the action signals strong enough.
And looking at the applications, it feels truly general purpose. They show high-fidelity simulation in classic problems like autonomous driving with new scenes.
Right, generating future video based on fine-grained vehicle controls.
But also, and this is huge for embodied AI, they show incredible results in manipulation video prediction.
Yeah, using RT1 data. We're talking about generating plausible videos of robotic arms grasping things based on controller inputs. This moves it beyond just a cool visual demo into a useful tool for training RL agents.
Right. They also showed complex stuff like real-time camera control and even multi-agent interaction, like one car overtaking another.
Where everyone maintains coherent, action-driven dynamics. It's really impressive.
So the overall conclusion is strong. Astra gives us a comprehensive framework that successfully unifies that high visual quality of diffusion with robust interactive control.
Across all these different domains, and we have to mention efficiency.
Right, because they kept the big diffusion model frozen.
Exactly. By relying on just the lightweight ACT adapters and the small MoAE experts, Astra gets this SOTA performance with the smallest parameter overhead of any of the models they compared it to. It's a very efficient path forward.
Okay, but despite this technical elegance, they did point out one major remaining challenge that future research needs to solve.
Yeah, inference efficiency.
Or how fast it can actually run.
Right. That's the trade-off. Because Astra relies on that fundamental autoregressive denoising, loop predicting chunk by chunk, generating a long video requires tons of denoising steps for every single new frame.
So real-time deployment is still a ways off.
For anything latency sensitive like online robotics control, it's still challenging. We'll need to see big advances in things like distillation or compression to keep this quality while cutting down that generation time.
That's a great challenge for our listeners to be thinking about. But if we connect this to the bigger picture, something really provocative.
Okay.
The paper notes that Astra's framework generalizes remarkably well to out-of-domain scenes. We're talking indoor photos, anime, even Minecraft gameplay.
And it still follows the actions faithfully.
Exactly. What does that suggest to you?
I think it suggests something really profound about the success of that noisy memory trick by intentionally weakening the model's reliance on just visual patterns.
And forcing it to use the action signal.
The model seems to be learning more fundamental domain-agnostic causal dynamics. It's learning how an action affects a system's state, not just memorizing visual statistics.
So it's learning a kind of primitive physics.
You could say that. And if we can keep pushing this architectural focus, reinforcing causal learning over visual dominance, then the next frontier for generative AI might not just be about scaling up image fidelity. It might be about developing architectures that inherently encode physics and causality into world models, making them robust, general, and truly capable of simulating our world under our instruction.